All right, this is section 8.3. This is called trigonometric integrals, trig integrals. That's a pretty generic name. We'll be looking pretty specifically at integrals with combinations of like sine and cosine and combinations of secant and tangent. The secant tangent stuff can kind of be extended and applied to like combinations of cosecant and cotangent. Those pairs have very, very similar sort of relationships. But in any event, to do this stuff, we're going to need a couple different trig identities, some of which you probably will have seen before from like a pre-calc, and a couple you maybe haven't seen yet. So let's just sort of recap those first, right? The first is our classic, what we call the Pythagorean identity, because it is kind of coming out of the Pythagorean theorem. And so that's sine squared of x plus cosine squared of x equals 1. So that's true whenever, right, you're sort of doing sine and cosine of the same value. You know, we're using x here, obviously for, you know, you could have thetas in there. It could be something a little bit more like a 3x or a 2x minus 5 or something. As long as the stuff that's inside the sine and the cosine matches, then if you do square plus square, you're always going to hit 1. So as long as those like inner values are the same, you're going to hit 1 when you sort of square them together. Coming out of that, what that means is you can actually kind of take this and then like solve it for sine squared. If you just like subtract the cosine squared over, what you get there is a nice way to kind of move from like a sine function to a cosine function, provided of course that it's a square. So sine squared would be the same thing as 1 minus cosine squared, which is just this rearranged, or from the cosine perspective, right, cosine squared would be the same thing as 1 minus sine squared. So that's just like two rearrangements of our original Pythagorean identity, and that's going to be something we use to kind of transition from sine functions to cosine functions, or vice versa. Another version of this is secant squared is 1 plus the tangent squared. So that's kind of a similar form, but obviously a little bit different sort of with secant and tangent and sort of where everything ends up. Essentially that's created if you take the original Pythagorean identity and you divide everything by cosine squared. Sine squared over cosine squared would be the tangent, cosine squared over cosine squared would be the 1, and then 1 over cosine squared, right? 1 over cosine is secant, so that would be secant squared. So you get this kind of, altered version of it in terms of secant and tangent, where you have now a way to get from sort of a secant function to a tangent function, and then of course this you could rearrange and subtract the 1 over, and you would have tangent squared would be equal to secant squared minus 1. Right. So all the ones we're going to be using really are the last four. We won't be using the initial Pythagorean setup quite so much. We're really using these like sort of variation and rewritten versions. The other thing we're going to use are called the half angle formulas, which is, it's kind of a weird way to name it, honestly. But essentially this is a way to get from sine squared down to a single version, in this case of cosine. So there's an interesting thing happening here where sine squared would be equal to 1 minus the cosine of 2x, the whole thing over 2. And so what's happening here is you're going from sort of an x on the inside to 2x. So you're kind of losing the square, but you're sort of doubling what the interior angle or the interior value would be. We're calling this a half angle formula rather than like a double angle formula. I guess it's just a matter of perspective in some sense. So going from a sine squared sort of down to a single cosine with obviously some extra pieces, but then also the interior angle changes. There's a cosine version as well. Cosine squared would go to 1 plus the cosine of 2x over 2. So what we're using here, right, all of these formulas are kind of based on subbing in identities for the squared version of a trig function. So we'll be looking for sine squareds, cosine squareds, right? Tangent, secant squareds. That's probably going to be our bread and butter in this section, based on what we're writing here initially. Okay. So what we're trying to do in general is two things. What I want to do first is we're trying to develop a strategy to sort of integrate, right? Evaluate the integral of sine to the m of x times cosine to the n of x with respect to x, right? dx. So this is essentially just like products of sines and cosines, right? So this could be like sine cubed and cosine to the 4. This could be, you know, sine squared and cosine to the 6. It could just be like sine to the 1 times cosine to the 1, right? We want sort of a generic strategy to be able to sort of solve and evaluate those integrals. And so obviously what's going to happen here is we're going to have to break down and rewrite these depending on what the different like powers are. In general, the goal is going to be a u sub with either u equal to sine x or u equal to cosine x. You're going to try to rewrite it using some of these identities, and your kind of goal is to try to get something where you can do a u sub, and you want to use as your sort of inside function either just plain old sine or cosine. So you want to end up with something, you know, u to the 5 times, you know, your derivative, right, where u is your sine x. So you're going to do that. Once you can get it in the form where you've got, right, sort of sine to the power times a single cosine, and then you would use u equals sine x. Or if you have cosine to the power and then like a single sine x, you would use u equal cosine x. This would work, right, because your kind of derivative of sine x would be cosine, your derivative of cosine would be negative sine, right? You have to deal with the negative there, but that's totally fine. The negative is not really a big deal. So the idea generically is you want to try to get from an integral that has, right, powers on both sine and cosine, you want to kind of shift it and rewrite it and rearrange it to get to something like this where you have just like sine to a power times a single cosine, or cosine to a power times a single sine. You want to be able to kind of use some of our formulas above, right, some of this stuff, to be able to transform yourself from both sine and cosine having different powers to you know, only having kind of one sine or cosine left over, and then the other one has all the power. So let's take something that's kind of in that form just as a starting point. And what I want to do is just sort of run this integral. This is, in theory, nothing super fancy. We've kind of done versions of this before. So I just want to kind of recap, you know, once we can get it in this form, like what the strategy would be here. So this is sine to the 5th times cosine x dx, right? And so the idea is you want to let your u equal sine of x, right? You want to use whatever's under the power, and you have this sort of single cosine left over, right? So then your derivative, du dx, right, would be cosine x. So dx, right, is du over that. And then as you start to sort of sub this stuff in, right, you've got your integral. So this is now u to the 5 times my cosine x, right? And then my dx becomes du over cosine x. This is just a pretty standard u sub. I feel like we've done versions of this before, right? Cosine will cancel cosine. So then this is really just the integral of u to the 5 du. So that's just a nice power rule, right? So that'd be 1 over 6 times u to the 6 raised to power divide plus big C. And so then rewritten 1/6, right? So then that's sine of x to the 6 plus big C. So generically that as a setup, it is totally fine, right? We can actually kind of solve that very quickly. You could imagine if I kind of flip the role here of sine and cosine, I could do something very similar, and that would also be fine, right? If I had the integral of, you know, cosine to the 4 times sine of x, right? I could let u equal cosine in that case, and I would get a very, very similar kind of answer. So then the question becomes not so much what to do if you have one of our functions here with an exponent and the other is just a single, the question really becomes, well, what if both of them have powers that are bigger than 1? So we're going to start to lay out a strategy for that. It'll depend on whether the powers are sort of even or odd. But that'll be what we sort of start to lay out in the next video. So that's kind of just the intro. So let's go. I'll see you in the next video.